All right, in section 10.5, we're going to talk about doing areas and arc length with polar coordinates. So we're going to use integration in order to calculate area of inside pieces of polar equations. And really, the interesting thing here is when you're doing area with polar equations, you're going to cut things into pie pieces instead of the regular rectangles. Now we'll look at a diagram of that in just a second. But basically, in our normal rectangular coordinate plane, the XY Cartesian coordinate plane, we cut things into rectangles. That's for a very specific reason. Well, in the polar plane, we're going to cut things into pie pieces. And then we're going to do a similar thing that we do with the rectangles. We're going to let these pie pieces get smaller and smaller and smaller and smaller, add them all up, and get the actual area of the thing I'm looking for. So let's check out a diagram of what I'm talking about here. What I've done here is I've sketched a line in both the polar coordinate plane and in the rectangular coordinate plane. And so remember, when we're trying to find area, in terms of doing a straight up integration, the area that I'm finding is the area between the curve and the x-axis. So let's say, by the way, this line is y equals negative 1x plus 2. So let's say I wanted to find an area, and let me see if I can get a good color on here, underneath this line and to the x-axis. Well, what we would do is we'd create a bunch of rectangles. I'm not gonna draw this very well with my cursor, but we'd create a bunch of rectangles, and then we'd take the limit of those rectangles as, let's say we wanted to find the area between 0 and 2. So we take all of these various rectangles, add up all that area, add up all the let the limit of the widths of these rectangles go to 0, add up those areas, keep getting better and better approximations, take the limit as those rectangles' widths go to 0, and you get the actual area under the curve. So that's the idea in terms of rectangular. Now, if you think about why we had rectangles, well, notice that those are the grid lines here on the rectangular coordinate system. So those rectangles had to be there because we were looking at a change in x as we did that. Our width of those rectangles were changes in x, or were various values for x's. So what's going to happen in the polar coordinate system is slightly different. So in the polar coordinate system, we don't have rectangular grid lines. What we have are these pie pieces. And instead of letting the width of x get smaller and smaller, well, we're going to have our angle get smaller and smaller. So what we do is we take a straight line to our curve, and then we draw basically a pie piece somewhere there. And then we do the same thing with the next line. Next line goes out, we draw a pie piece. And then we go to the next line. Next line goes out, we draw a pie piece. Now I didn't draw this pie piece very well, but you guys get the point. We're getting a bunch of little pie pieces, and then we're going to let the angle change in angle get smaller and smaller and smaller and smaller. And you can see that that is also going to add up to the same area that we have here. So all we have to do is figure out, well, what's the area of a pie piece? And then as those pie pieces get thinner and thinner and thinner, add them up, that gives me my integration. Question becomes then, how do I calculate the area of a slice of a pie piece? Well, if you think about a pie piece, let's think about this right here. So, whoops, straight line from the origin along the polar axis or the x-axis, and also a straight line at the angle of pi over 6. Create this pie piece here. Hopefully you guys understand what I'm saying. This pie piece here. Fill that in a little bit. Well, notice that it's just a part of a circle. And so all we have to do is figure out the radius, square it. Now, the whole area of a circle, the entire area of a circle, is pi r squared. So half the area of a circle would be 1/2 pi r squared. Notice that that pi, or excuse me, the angle that we went, if we went an angle all the way around this circle of 2 pi, the area of the circle is pi r squared. If we went out an angle of pi, the area of a half of a circle is 1/2 pi r squared. If we go out an angle of pi over 6, well, it's going to be whatever 1/2 times pi over 6 r squared. In other words, the area is just going to be how many radians I covered multiplied by 1/2 times r squared. Hopefully that makes sense. And by the way, that's why we always use radians. That's one of the reasons we always use radians when we're dealing with polar coordinates, is so it translates that area of a circle into just half of the distance that I've went around. So that's the idea there. Now, how that translates into an integration, pretty straightforward. If you cut things into pie pieces instead of rectangles, then the area of the region that we're looking at is 1/2 integrate from alpha to beta, where alpha is our starting angle and beta is our ending angle. Our function squared. This is our radius squared. So it's 1/2 radius squared, and then the angle that we're covering from alpha to beta. And we're covering the little chunks of them, obviously adding all those up. Usually, a lot of people will force alpha and beta to be between 0 and 2 pi. That's not completely necessary, but you could have alphas being negative angles if you wanted to. You could have betas going above 2 pi if you wanted to. But generally speaking, we have an interval of alpha and beta. We don't want it to exceed 2 pi because that wouldn't make sense. So let's do some calculations. Let's take our rose curve that we saw earlier, or a rose curve that we saw earlier, and let's try to find the area of one petal of this rose curve. R equals 4 cosine 3 theta. Now I'm going to graph this because that's going to be a very important part, the most important part of this whole operation, okay? But before I graph this, let me just go and set up the integration first. As we calculate area here, we have our formula that we just saw, 1/2 alpha to beta, our function squared. Now our function is 4 times cosine 3 theta. So all we have to do into this part, notice there's nothing fancy there, it's just the function itself, 4 cosine 3 theta. Now, we have to figure out, and this is the hard part, the alpha and the beta if we're trying to get one petal of that rose curve. So let's go ahead and do that. What I've done is I've graphed 4 cosine of 3 theta in polar form, and I need one of these petals. Now, if you followed how you graph this, by the way, You can graph this on your calculator as well. It's actually probably better on your calculator than it is with Desmos right here because it's easier to trace around and see where your petals start and where they end. So if you start at angle theta equals 0, you'll find that you're ending up at this point here. And you start tracing over until you get to, well, what we would call the origin. And then it traces out this lower left petal. And then it traces out this upper petal. So what I would do is I would say probably, well, when do we hit the origin? And then when's the next time we come back around and hit the origin? Okay. So when do we hit the origin first? And then when do we come back around and hit the origin? In other words, when do we get radius equals 0? And then when do you come back around and get radius equal to 0 again? Now, you can deal with your calculator and try to use the trace key to trace that out. You can also do this algebraically. You can say, well, when is, whoops, excuse me, when is 4 cosine of 3 theta equal to 0? And we should know, hopefully, that when is cosine 0? Well, cosine of an angle is 0 when that angle is, well, it's pi over 2, 3 pi over 2. Let's do that. Pi over 2 when the angle is 3 times pi over 2, when the angle is 5 pi over 2, and so on and so forth. Any sort of, you can just keep adding pi to each of these angles and you figure that out. So basically, what our angle is, obviously this 4 is going to go away, divide both sides by 4. Our angle is 3 theta. So if you think about this, when is 3 theta equal to pi over 2? When is it equal to 3 pi over 2? When is it equal to 5 pi over 2? We'll just divide both sides by 3. So the first time we end up hitting the origin is at pi over 6, and then the second time is at 3 pi over 6. By the way, that's pi over 2 when you reduce that fraction. So hopefully that makes sense. Again, if you want to trace out using your calculator trace function and see that as the first time as you trace over here, you should get pi over 6. Obviously, it'll be maybe in decimal format. Trace it around. The next time it comes back around and hits the origin, you're at pi over 2. So what that means is I can go back up, and if I'm going to find the area of one petal, I can start at pi over 6 and go to 3 pi over 6, which again is, I'm going to call just pi over 2. I'll reduce my fractions there. And at this point, all we're going to be doing is plugging this into our calculator. So area is going to be equal to whatever we get out when we plug that into our calculator. When I plug that in, my calculator gave me about 4.19 when I rounded it to 2 decimal places. So that's the idea, about 4.19. By the way, make sure your calculator, once again, is in radians mode. It's very important that it is. My calculator was still in polar mode, so that's why when you saw my screen, my variable was in theta. All right. But the important thing is make sure your calculator is in radians because otherwise it's going to mess the whole calculation up here. All right, so the area is about 4.19. So what I'd like you to do is push pause on the video and try to find the area of one petal of r equals 6 cosine of 4 theta. Push pause and try to do that. So we start out by saying A is equal, the area is going to be 1/2 alpha to beta integrated f theta squared d theta. Obviously, our function is 6 times cosine of 4 theta. That's a rose curve with 8 different petals. We just now need to figure out what the alpha and the beta need to be. You can do this by graphing and then trying to figure out how that's going to work. All right, at 0, you start out here, you trace around. The first time you hit, second time you hit, third, fourth, you just keep going and going and going on each case. But by the way, this is something I didn't mention last time either, but it is true that each of these petals is exactly the same as far as area of the interior of the petal goes. So it was okay no matter which petal you pick to trace. So I like, again, origin to origin. First time it hits the origin, go around. Second time it hits the origin. First time it hits will be my alpha. Second time will be my beta. All right. You can do that algebraically too for the exact same reasons. Um, 6 cosine 4 theta, when is that 0? Well, obviously dividing by 6 isn't going to do a whole lot. I can divide both sides by 6. That doesn't change a whole lot. We know cosine is 0 when my angle is pi over 2, when it's 3 pi over 2, all that kind of stuff. So cosine of 4 theta, well, oops, when is 4 theta equal to pi over 2? When is 4 theta equal to 3 pi over 2? All we have to do is divide everything by 4. All right, so pi over, oops, did I say that? 4 times 2 would be 8. So 3 pi over 8, 5 pi over 8, 7 pi over 8, etc., etc., etc. So that's the idea there. So in order to go from one to the other, just take, well, we're going to start at pi over 8. We're going to end at 3 pi over 8. So we're going to start at pi over 8, and we're going to end at 3 pi over 8. Okay, go ahead and plug that into your calculator, and you'll get the answer. Now, I want to mention a couple of things. First off, just as we calculate that, you get 7.07. But remember that we did trace the first time we hit the origin to the second time we hit the origin with this leaf. We got 7.07, but we could have just as easily said, actually, I wanted to take the petal that was the second or third petal. So I could have jumped from 3 pi over 8 to 5 pi over 8, and that would have just given me a different petal. Hopefully that makes sense. In other words, what we did here, the first, you start out here at 6, 0. As you trace around, the first time you hit the origin, you go through the origin, you get that pi over 8. As you go around, you hit at 3 pi over 8. So what we traced out was this petal here. Well, if I'd have started at 3 pi over 8 and went to 5 pi over 8, I would have traced out this petal here. So each jump from sort of origin to origin represents another petal. So if you would have integrated from 3 pi over 8 to 5 pi over 8, you would have also got the exact same number. If you would have integrated from 5 pi over 8 to 7 pi over 8, you would have gotten the exact same number. And that's what I did here. You can see that on my calculator. I integrated from pi over 8 to 3 pi over 8. I got 7.07, 0.068, blah, 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 blah. If I would have gone to the other petal, 3 pi over 8 to 5 pi over 8, you would have gotten the exact same number. And so that's the area of one petal of this polar equation. So we've dealt with a couple of rose curves. Let's move on to the cardioids and the lemnicons and all that kind of stuff. So the first example, I want you to try this on your own. Find the area of the region bounded by r equals 3 minus 2 sine theta. Go ahead and graph it and see what you would integrate to and from. All right, so 3 minus 2 sine theta. Well, what's happening there is not the same thing as what we had earlier. There's not a whole lot, um, how do I say? There's not a whole lot of petals or anything. It's actually just one unit, but the actual area is pretty straightforward. 1/2 integrate from alpha to beta, the function squared. Our function's obviously 3 minus 2 sine theta. So we just got to find the alpha and the beta, the angle of start and angle of finish. So if we do that, well, it's nice to graph it. I'd graph this on your calculator if you can. Otherwise, that's fine. Now, obviously, we can't count from where this curve hits the origin to where the curve hits the origin a second time because this curve never hits the origin. So if we were to try to do this algebraically, you wouldn't want to write r equals, you wouldn't want to solve this for equaling 0. You could solve this for equaling 3, right? 3, we do hit the point 3, 0 in both cases. But so you could do that algebraically there, but it's easier to just hit trace on your calculator and trace this around and see that as it goes around all the way around. It'll start at 0 here and it'll go all the way around and end up at 2 pi. So that's what we're going to do. We're going to integrate this whole thing where from 0 to 2 pi. Now just plug this into your calculator at this point. Hopefully you get the same thing I did. I got 34.56 as the area. Again, you could do this algebraically, but it's a little bit more difficult and it's probably not worth it to do algebraically. So there you go. Tracing works best in that case. Now in our last example, we got a lemnicon with an inner loop. And so what I'd like you to do is try to think through how you would find the area of the inner loop of r equals 2 minus 4 cosine theta. So graph it, use trace, find the alpha and the beta that you need. Now, if you graph this, the key thing here is that the graph actually starts at where my cursor is sitting here. So if you try to trace that using your calculator, you'll see when theta equals 0, we're at the rectangular point -2, 0. And as you start tracing around, the first time you hit the origin is at theta equals pi over 3. And then you start going around and around, around, around. And the next time you hit the origin, you're at, well, 2 pi minus pi over 3. And you hit 2 pi once you go back to the point, the rectangular point, -2, 0. So basically, we got pi over 3, and then you go all the way around, and 2 pi minus pi over 3, which is, what is that? 5 pi over 3. So 5 pi over 3 and pi over 3. Now that's actually a problem for us, because if you start at pi over 3 and you go all the way around till you hit 5 pi over 3, you didn't actually travel along the inner loop. You traveled along the outer loop. So that's going to give you the area inside this whole thing if you start at pi over 3 and go to 5 pi over 3. So what we need to do is we need to extend our availability for alpha and beta, okay? So we either have to extend the alpha into the negatives, or we have to extend the beta above 2 pi. So hopefully that all makes sense. I'm going to let my alpha go into the negatives. Hopefully you understood why I called this the first time 2 pi minus pi over 3, because notice that negative pi over 3 is going to be at this origin as well. So if I start at negative pi over 3 and then I increase until I hit theta equals 0, and then I go from theta equals 0 to a positive pi over 3, I will have traced around that inner loop one single time. All right? Hopefully that makes sense. So basically, my area, we go 1/2 integrate 2 minus 4 cosine theta squared. My alpha, the easiest thing to do is to do negative pi over 3, and my beta as a positive pi over 3. So once you do that, you just type that into your calculator, hit enter, and get the answer. I ended up with about a 2.17 as my answer. So about 2.17 is the area of the inner loop. You can play around with that, get the area of the outer loop as well if you want. Okay, hopefully that all made sense. So anyways, that is how we figure out areas using the polar form. And by the way, we are doing areas. This is slicing into nice little pie chunks all the time. So with this is the last few examples have been really beneficial to find area inside a petal. Those would have been extremely difficult by trying to find areas using the rectangular forms.